Hi guys, so in today's video we're going to look at answering question 4 from the statistics section of the paper 3 Edexcel exam from 2022, so last year's exam. So hopefully doing this question today will help you prepare for paper 3 next week. So this is again 2022 paper 3 in the stats section of the Edexcel A-level exam. So we're going to do question 4 today. So we've done question 6 and question 5 from this exam, but let's have a look at question 4. So a dentist from past records knows that 10% of customers arrive late for their appointment. Okay, so a new manager believes that there has been a change in the proportion of customers who arrive late for their appointment. So we're going to take a random sample of 50 of the dentist customers. So the first part of the question says, write down a null hypothesis corresponding to no change in the proportion of customers who arrive late, and an alternative hypothesis corresponding to the manager's belief. Okay, so with this question here, so I mean, this is again kind of like a hypothesis testing question, but they're kind of guiding us through this one rather than just like forcing us to do it on our own. So with this one, we've got essentially what we've got here is you've got a binomial distribution. I guess that's the first thing to notice. So I mean, you've got a sample of 50. So if we call x, let's define x to be, so x, capital X, is going to be the number of customers in the sample. So in the sample who arrive late. So what we've really got here is we've got a binomial distribution. So we'll just make a note of this in the question here, that this is a binomial distribution. So binomial. Now, how many people do we have in our sample? We got 50. So 50 as your n value. And assuming H0, so assuming our null hypothesis, the probability of success, the proportion of customers who arrive late, that's going to be 0.1. And again, this is assuming our null hypothesis. So again, if we call P, so remember with these hypothesis testing questions, it's good to always define your variables. So always give a definition for every new letter that you introduce. So P, I'm going to call P the proportion. So P is going to be the proportion of, I'll just make that I a bit neater, a proportion of customers who arrive late to the dentist, So yeah, so our H0 is going to be P equals 0.1. So H0, so our null hypothesis is the initial previous belief that the from what the data showed before, that 10% of customers arrive late, so 0.1 as a proportion. And then our alternative hypothesis, so this is where we just have to interpret the question. So a new manager believes that there has been a change in the proportion of customers, so not an increase, not a decrease, a change. So P not equal to 0.1. So I guess the key thing to note now is that this is going to be a two-tailed test, isn't it? So this is now a two-tailed test. Okay, so now let's go to part B. So part B, using a 5% level of significance, find the critical region for a two-tailed test of the null hypothesis in A. You should state the probability of rejection in each tail, which should be less than 0.025. Right, so again, we've got this two-tailed test, and we've got a 5% significance level. So let's just make a note of this here. So we've got 5% sig level. And it's a two-tailed test, That means we need to split significance level in half. So split sig level, I just call it SL for sig level. So split significance level in half. So 2.5% in lower tail and 2.5% in upper tail. So, I mean, let's try and explain this just in case you guys are a bit you feel a bit stuck with this kind of idea. So remember what a significance level actually is. So again, I think a lot of students kind of they don't really understand what a significance level is. So a significance level is something that as statisticians you decide. So it's an arbitrary thing, or what the examiner in your exams, what the examiner will decide. So it's an arbitrary thing. It's a probability. So when you do these experiments where you collect data and then you see whether there's been a change in your probability, or whether your data suggests there's been a change in your probability, the idea is that the significance level is the probability you choose of rejecting H0. So assuming that your null hypothesis is true, we're going to arbitrarily suggest that, or we're going to arbitrarily conduct an experiment where we've got a 5% chance of rejecting the null hypothesis. We've got a 5% chance of rejecting our initial belief. So we keep that probability low because obviously, you know, if we collect the data and we got a number from our data which has a low probability of occurring, a really low probability, then it would suggest that our initial null hypothesis must not be true. So the idea of these questions is that what we're doing is we're setting up a probability of rejecting H0 to be quite low, so in this case 5%. And if we collect our data, so we're talking about customers who are being late for their appointment here. So let's say we collect our data, we've got 50 customers who we're going to take in our sample. And let's say, I don't know, let's say we pick from our data, 50 people, 2 of them were late for their appointment. So what you want to do is you want to calculate the probability that 2 or less customers are late for their appointment. And if that probability is really, really low, so lower than this significance level probability, I mean, this is a two-tailed test, so we're actually splitting it in half, but we'll see in a minute what we're doing with this. But if that probability of getting 2 or less patients, for example, is less than this significance level, then we reject H0 because that probability, the probability of getting what we got from our data was so low, it suggests that our initial assumption can't be true. So it would suggest that our initial assumption probably is incorrect. So that's the idea behind significance levels. So hopefully that gives you a bit of foundation again to what these significance levels really are and what these hypothesis tests really are. So let's think about this. I mean, you don't need to write this down in your answer, but let's think about really what we've got going on here. So we've got a binomial distribution if we assume H0. So again, assuming H0, assuming H0. We've got this binomial distribution, so x binomial 50 is 0.1. So the way this works, obviously binomial distribution, we're thinking about discrete data. So if we draw like a little graph here, so the x-axis is going to be the number of customers who arrive late to work, arrive late to their dentist. So customers who arrive late. So we've got a sample of 50. I'm not going to write out 50 on the x-axis here, but 1, 2, 3, 4, I think I'll just stop there, so on and so on, so on, so on, all the way up to like 48, 49, 50. So obviously this is discrete data, so you could have 0 customers being late, 1, 2, 3, 4, all the way up to 50 in our sample. So I'll just write this number 4 again. So if we call the y-axis probability, so the probability that you get 0 customers being late, probability that you get 1, 2, 3, 4. So you're going to have like a graph like this essentially. So you're going to have like a graph like this, maybe like that, and then yeah, obviously different numbers, different probabilities down here. Maybe it's getting smaller and smaller and smaller like this. My lines don't really fit with my x-axis, but it doesn't really matter. So right, we got this graph of probabilities here. So I mean, it's just like a rough sketch, obviously not accurate. So the idea obviously is that probabilities all add up to 1. So all of these probabilities here, all these heights here, if you add them all up from 0 up to 50, you get 1, because obviously probabilities add up to 1. So we've got 100%. So you add up all the heights, all the y values, you get 100%. So if we're doing a 5% test, a 5% two-tailed test, remember 5% two-tailed test, we're splitting the 5% into half. So we're splitting 2.5% on the lower side, so 2.5% on the lower end, and we're splitting 2.5% of the probability of rejecting H0 on the upper end. So the idea is what we're going to do is, I mean, we're going to use the calculator to do this, but the idea behind it is you're basically adding up these areas there until you get, well, not areas, sorry, heights, because we're dealing with discrete data, I should say heights. So we're adding up the heights of these line charts. So this is like a line chart. You can think about it like a bar chart. So we're adding up the heights of this until we get 2.5%. And then basically the numbers that give us, so when we add up these heights of these, again, like, you know, quote bar charts, when we add up those heights until we get up to 2.5%. So I mean, let's just say, for argument's sake, that you add up probability that you get 0 customers arriving late, probability that you get 1 who arrives late, probability that you get 2 who arrives late. So let's say you add up those probabilities there, and then let's say that gives you something like 2.5% or less than 2.5%, then the critical region would include 0, 1, and 2. Because those probabilities, when you add up those probabilities, it's less than 2.5%. And let's just, for argument's sake, say a similar thing down here. So let's say you add up the probability that all of your customers are late, plus the probability that 49 are late, plus the probability that 48 are late. And let's say that when you add those up, you get 2.5%. Then again, these would be on our critical region here. So 48 would be in the critical region, 49 and 50 would be in the critical region there. So that's kind of how this works. Now, obviously, what we're going to have to do to work out this critical region is we're going to have to use the inverse binomial function on the calculator. So inverse binomial function. So similar to like the inverse normal function on the calculator, which gives you critical values, or which gives you values on your x-axis of your normal distribution, we want to use the inverse normal distribution, and that's going to give us these values on the x-axis that we need, these critical values. So what we're going to do, so we've got 2.5% on the lower tail, so this is our lower tail here, so LT, and this 2.5% is devoted to the upper side of our distribution. So again, the extreme value, so we've got a 2.5% probability of rejecting H0 if we get numbers in our data which are really small, so like a small number of customers who arrive late, and then we're dedicating 2.5% of the probability of rejecting H0 to the upper tail, so big numbers of customers who arrive late. So what we're going to do, so let's focus on our lower tail first, so the lower side of this distribution of customers who arrive late. So let's look at our lower tail first. So what we're going to do is we're going to go to the inverse normal function, inverse binomial function on our calculator. Let's go to binomial, inverse binomial. And what we want to do is we want the area. So when it says area, I mean, it's kind of very similar to normal distribution. I mean, obviously with this line chart here, or this bar chart, however you like to think about it, these aren't areas, these are heights of a graph, but you can think about them as areas basically. I mean, you could kind of, if you really want to think about it like this, you can kind of use like a line to join up this there, and then you can think about it like a normal distribution, even though a binomial distribution is obviously different. Your area is going to be 0.025. So remember how the calculator works. The calculator is programmed to take areas on the left tail, the left side of your distribution. So if you want an area on your lower tail to be 0.025, 2.5%, you just want to put 0.025 as your area into your calculator. So your number of trials, so your n value number of trials, well, that's going to be 50. So we've got a sample of 50. And your probability of success is 0.1. So we're going to put these data into the calculator, 0.025, number of trials 50, p-value 0.1. We're going to execute that. And then what we get is we get a value of x equals 1. So the output gives us x equals 1 there. Okay, so what does that tell us? So we just got to be careful with this. So what that's telling us is that we've got so we've got so when we put this number into the calculator, this area is 0.025, we get a value of x equals 1. Now, what we've got to do, just to be careful, because we're using a discrete distribution rather than a continuous distribution with continuous numbers, is we just got to go to the binomial CD now and check whether that gives us a value bigger than or less than 0.25. So what we need to do now, so yeah, we got this lower value x equals 1. Now that doesn't mean that is the critical value, just because we're dealing with discrete data. So we're not dealing with continuous data, we're dealing with discrete data. So the way the calculator works is that it rounds to the nearest number. So it's gonna, you put the area in like this, 0.025, but just because we're putting in an area 0.025 in the calculator doesn't mean the height of these bars exactly add up to 0.25. What the calculator does is it rounds this area to the nearest number on the x-axis there. So it rounds it to the nearest number. So what it does is it rounded it to 1. Now that doesn't mean that 1 is in the critical region. It just means that when you put the area of 2.5% into the calculator, it rounded the number to 1. So, I mean, if we think about a line, let's try and do this properly, because I want to make sure you guys understand this. So we got 0 there, 0 customers who arrive late, 1 customer who arrives late, 2 customers who arrives late. So what the calculator did, I mean, you've got a height here for the probability that 0 arrived late. So you've got that height here, there. You've got this height, let's say there. So just because we put 0.025 into calculator doesn't mean that these two heights added up there equals 0.025 exactly. It just means that the nearest thing, so the nearest x value, so the nearest number of customers who arrive late closest to this area, 0.025, is 1. So again, what the calculator kind of does is it kind of just approximates this using a curve, and it says, well, okay, well, the area there is 0.025, or it may be over here, maybe this total area there. It just rounded a number between 1.5 and 0.5 to 1. So that doesn't mean that 1 is in our critical region. So hopefully that made sense, because obviously I just want to make sure you guys really understand these hypothesis tests, because they can be difficult to understand. So I'm just going to rub out this diagram here because this is a bit of a mess. Okay, right. So that's the idea of what's going on here. So what we want to do now then is we want to go to our binomial CD. So go to binomial CD. I'm running out of room now, unfortunately. Binomial CD. We want our x value to be 1. We want our, because what we want to do is basically work out the probability that x is less than or equal to 1. So if this probability is bigger than 0.025, then 1 is not in our critical region. But if it's less than the significance level, so if it's a really tiny probability less than that significance level, so less than 0.025, then we would reject the null hypothesis. So it would be in our critical region. Again, your p-value is 0.1, number of trials is 50. So when we put this into the binomial CD section of the calculator, x equals 1, number of trials 50, probability 0.1, we get a probability of x being less than 1 or equal to 1 to be 0.0338. Now that's actually bigger than 2.5%. So 1 is not in our critical region because this probability is too big. It's bigger than the critical 2.5%. So it's still, I mean, it's a small probability, but it's bigger than that critical significance level probability. So 1 is not in the critical region, but 0 must be, because we know from the inverse normal calculation that we've got, well, technically a critical value in speech marks of 1, but we just saw from the calculation here that 1's not in the critical region because it's actually bigger than, sorry, I shouldn't put a dot there. Let me get rid of this dot there. It's actually bigger than 2.5%. So we know, therefore, x equals 0 is in, sorry, let me write this again. So x equals 0 is in the critical region. So it is in critical region. So I'll just put like a circle around that. So that's the lower tail of our distribution. I'm going to have to go down here to the next question because I'm running out of room. But the upper tail, so now let's look at our upper tail of the distribution. So upper tail. So again, with this side, now if we go back to our diagram here, so remember, we're going to go back to inverse binomial. So we want to go to the binomial section of a calculator, go to the inverse binomial function. Now this time we're looking at the upper tail of the distribution, so the upper side of our distribution. So now the area, when we put our data into our calculators, kind of like what we did here, I'll just do like a big bubble just to emphasize that was our lower tail. So now with our upper tail, we'll do this down here. Again, it's the same thing. We're going to use the inverse binomial function in the calculator. Our area is now going to be 0.975. So 1 take away 0.025. Because remember, the area in your calculator, the way your calculator works is it takes areas on the left side. So really what we want is we want this area to be 0.975 instead. Because again, the area, the way the calculator is programmed is it takes areas on the left side of your distribution. So you want the area on the left side of the distribution to be 0.975, so 97.5%. We want, so that's our area. Obviously, again, n value 50, p value 0.1. Now let's put this into calculator. So 0.975, n 50, p 0.1. And what we get is we get an x value of 9 again. Right, so now what we've got to do now is the same thing that we did before. So what we need to do is we need to work out the probability. So now we're looking at the upper side of the distribution, so the upper tail. So what we want to do is we want to do the probability that x is bigger than or equal to 9 this time, because now we're looking at the upper side of things, at the upper end of the distribution. So we're looking at values greater than a potential critical value. So now again, we're going to use binomial CD to do this. So accumulating, so remember binomial cumulative distribution. So we're accumulating probabilities, we're adding up probabilities. So that's the way that I think about it. So again, N50, P 0.1, and your X value. Well, actually with this one, so I've made a mistake here, because again, what we want to do is 1 minus. So 1 minus the probability that X is less than or equal to 8, because obviously, again, the calculator, the binomial CD function, your calculator takes areas to the left side of your distribution. So we're going to go to binomial CD, 1 take away, and then you want your X value in your calculator to be 8, N to be 50, P to be 0.1. I'll just put brackets around that. Let's see what number we get. So x8, n50, 0.1. So we get this here. So 1 minus 0.942. Now, if we do 1 minus that in the calculator, 1 minus answer, we get 0.0579. Now that's bigger than 2.5%, isn't it? So that's still bigger than 2.5%. So we know that 9 is not in our critical region because the probability that x is bigger than 9 is too big. So that means that 10 is going to be our critical value. So 10 must be our critical value, because remember, the inverse binomial function, the calculator, gave us an x value of 9. But the probability, assuming h0, the probability that you get 9 or more customers who turn up late was about 5%. That is bigger than 2.5%, the 2.5% significance level. So it's too big. So that means that the probability that x is bigger than or equal to 10. So the probability that 10 or more customers turn up late must be less than 2.5%. And we know that from the calculator, the inverse binomial function, the calculator. So that means that x equals 10, 11, 12, 13, 14, 15, 16, all the way up to, and I can't be bothered to do any more of this, all the way up to 15. That will be in our critical region. So our critical region, I know I've made a mess of this question because I've run out of room, but our critical region, if I just write this, I'm going to just write it down here. So our critical region, is going to be this set of numbers here. So it's going to be the set 0 and also 10, 11, 12, 13, ... all the way up to 50. So we can just say 0, we'll just write it like this. So 0 and all integers from 10 to 50. So that would be our critical region there. So that's our critical region. And if we just go back to the question as well, so you should state the probability of rejection in each tail. Right, so let's do this part now as well. So the probability, so we've got on the lower side of the distribution 0, and on the upper side of the distribution 10, 11, 12, 13, all the way up to 50. So the probability that x is less than or equal to 0. So this is what the question wants us to find out. So let's work this out. So again, we're going to go to the binomial CD section of the calculator. So binomial CD, x is going to be 0, number of trials again 50, probability 0.1. So this is the binomial CD function again. If we do this in the calculator, what do we get? So we get, 0.00515. Okay, so the probability that you got 0 customers who turn up late is about 0.5%. Now let's look at the upper side of our distribution. So the probability that x is greater than or equal to 10. So that was our lower side done. Now we want to look at the upper end of our distribution. So now we're going to do, again with the calculator, remember the areas are on the left side of the distribution. So we've got to do 1 minus the probability that x is less than or equal to 9. So 1 minus, and then again, binomial CD function on the calculator, x equals 9, n equals 50, p equals 0.1. So it's going to be 1 minus and then x9, n50, p 0.1, we get this here, so 0.9755. So 1 minus that, so 1 minus answer, so we get 0.0245, which is obviously less than 2.5% as we hoped for. So we know for a fact that the critical region is definitely 0, 0, 10, 11, 12, 13, all the way up to 50. So we know that for a fact. So what is the actual significance level for this test? So let's just go back to the question again. So yeah, the question says, you should state the probability of rejection in each tail, which should be less than 0.025. I mean, we've done that already. We just actually done that in there. So the probability of rejection in the lower tail, so probability of rejection in lower tail is that number there. And the probability of rejection in the upper tail is this number there. So we've got a 0.5% chance of rejecting the probability in the lower tail. So that would be your lower tail probability. And we've got a 0.0245 probability, so a 2.45% chance of rejecting H0 in the upper tail of the distribution there. So hopefully that makes sense. So what you would write down is you write down, this is the probability of rejection in the lower tail. So lower tail rejection probability. And what I'll do is I'll just put brackets around that there just to emphasize that. And then this is the upper tail rejection probability here. So 0.45. So upper tail rejection probability. Okay, great. So we've got that those two probabilities there. So I know I've taken a long time with that question for a 3-mark question, but I just think it's really important you understand these hypothesis tests and how you do these properly, because a lot of students don't really understand them. So part C, so find the actual significance level of the test based on your critical region from part B. So with this one, this is quite a simple one, actually. We just want to add up the two probabilities that we got. So that probability plus this probability. So you just add them up. So with part C, I mean, I'll write part C down here, and I'm skipping to the next, this question 5, but the actual significance level, so actual significance level is equal to the probability of rejection in the lower end, so 0.00515, and then plus the probability of rejection, so the significance level that we actually have in the upper side is 0.0245. If we work that out on the calculator, so plus 0.00515. So yeah, the actual significance level for this test is actually really 0.0297 to 3 significant figures. So that's really our, so actually, well, we said it was a 5% test, but actually, because we've got discrete data, we don't, as I was trying to explain before, when you add up the areas of these of the bars in this line chart, obviously you're not going to exactly get 2.5% on either side. You're going to get different numbers. So the actual numbers you get when you add up all the probabilities in your critical region is actually this there. So that's actually the real significance level to this test. Actually, exactly. So that's part C. And then part D, so the manager observes that 15 of the 50 customers arrive late for their appointment. So we've referenced part B, comment on the manager's belief. Right, so now we know from the critical region that we got in part B, we know that our critical region is 0, 10, 11, 12, 13, and up to 15. So if we collect our data, so we got a sample of 50, we've collected the data, and 15 of those customers arrive late. Now, 15 is in the critical region because obviously, you know, we've got 0, 0, 10, 11, 12, 13, all the way up to 50. 15 is obviously in that set of critical region values. So with part D, what we want to say is that 15 is in critical region. So it's in our rejection region, basically. So it's in our critical region. So therefore, we need to reject H0. So we're going to reject our null hypothesis. So therefore, sufficient, so there's going to be sufficient evidence to suggest that proportion of customers who arrive late, so proportion of customers who arrive late is different from 0.1. So the key thing with this one is obviously this is a two-tailed test. So we don't want to say, oh, there's sufficient evidence to conclude that the proportion is bigger. We just have to keep consistent with the alternative hypothesis and say that there is sufficient evidence to suggest that the proportion of customers who arrive late is different, because that's what we're testing. We're testing whether the proportion is different. So I know, you know, we got 15, which is so 15 customers arriving late. Now that is in the upper end of the distribution, because as we can see from the critical region that we got here, 15 is in the upper side. So this is the upper end, this is the lower end. But because we're testing whether we're testing the null hypothesis against the proportion being different from 0.1, that's what we want to say in our conclusion. So sufficient evidence to suggest the proportion of customers who arrive late, is different from 0.1. So that's our conclusion. Remember to always give a conclusion in context, because obviously we need to do that. We just need to make sure that the conclusion we give is in the context of the question. So that would be that question there. So quite a tricky one. I mean, part B is quite a tricky one, just making sure you get your numbers right in your calculator and using the inverse binomial function to get the right critical region. So just be aware of those kind of questions. But any questions, drop them in the comments. And if you do need any one-to-one tuition over the next few days, remember you can drop me an email. So if you need one-to-one tuition, and the price that I charge, £35, email me Dr. Differentiation as in doctor, and then differentiation as in like differentiating functions, at Gmail. So gmail.com. So do drop me an email if you do want any last minute one-to-one tuition. I've done a video on this and I'll link that in the description below, where you can find out more details about me and how the sessions work. But do drop me an email if you do need any help. So yeah, good luck with your revision, and hopefully paper 3 goes well.